Picture this. It's 1976, and every performance engine in America is running either a Holley 4-barrel or a Rochester Quadrajet. These are the kings, the untouchables. Then Ford's engineers walk into a dyno room in Dearborn with something that looks like it was designed by a watchmaker who'd never seen a carburetor before. It has sliding ventures, no jets, and a fuel metering system so elegant that Holley's engineers would spend the next decade trying to figure out how Ford did it. This is the story of the variable Venturi carburetor, the trick that quietly embarrassed the carburetor establishment and then disappeared into history. Chapter 1. The Carburetor Wars of the 70s. Let's rewind to the early 1970s. America's automotive industry was in full panic mode. The Clean Air Act had just dropped on Detroit like a nuclear bomb. Suddenly, engines that had been happily spewing hydrocarbons for decades needed to meet emission standards that seemed physically impossible. Carburetors, which had changed very little since the 1930s, were being asked to do something they were fundamentally terrible at: precision fuel metering across every possible operating condition. The carburetor establishment had a response to this crisis, and it was basically to throw parts at the problem until something stuck. Holley added vacuum secondaries, accelerator pumps, and enough emission control vacuum ports to look like a spaghetti factory exploded. Rochester's Quadrajet became this bizarre hybrid of small primaries for economy and massive secondaries for power, all controlled by a labyrinth of springs, air doors, and prayers. Did they work? Kind of, sort of, if you squinted and didn't think too hard about it. By 1976, the carburetor market in America was essentially a duopoly. Holley owned the performance market. If you wanted to go fast, you bolted on a Holley. End of discussion. Rochester, specifically their Quadrajet, dominated the OEM market. General Motors put Quadrajets on everything from Chevettes to Cadillacs. Even Ford was using Holleys and Motorcraft versions of various designs under license. It was settled science. These were the only two ways to meter fuel. Everyone knew it, everyone accepted it, and everyone was wrong. Chapter 2. Why everyone said it couldn't be done. Here's why everyone said improving the carburetor was impossible. A carburetor works on the Venturi principle, which is fancy physics talk for make air go fast through a restriction and it sucks fuel along with it. The problem is that a fixed Venturi, which is what every carburetor used, is a compromise. Make it small, and you get great fuel economy and throttle response at low speeds, but the engine chokes at high RPM because not enough air can get through. Make it big, and you get great top-end power, but terrible low-speed drivability and fuel economy because the air velocity is too low to properly atomize the fuel. The jet system was an even bigger nightmare. Jets are basically precisely drilled holes that meter how much fuel gets sucked into the airstream. But here's the problem. One jet size. Every operating condition: idle, cruise, wide open throttle, cold start, hot restart, altitude changes, one fixed orifice trying to be correct for all of that. It's like trying to paint the Mona Lisa with a roller brush. Technically possible, but you're going to have a bad time. Holley's solution was multiple jets, multiple circuits, power valves that opened under certain conditions, accelerator pumps for transients. The Quadrajet added variable area secondaries controlled by airflow. These systems worked, but they were band-aids on a fundamental design flaw. And they required constant tuning. Change your altitude by 1,000 feet? Yeah. Better rejet. Install a different cam? Rejet. Sneeze wrong? Probably should rejet just to be safe. Detroit accepted this because, well, what choice did they have? Fuel injection existed, but in the mid-70s it was either unreliable mechanical systems that cost a fortune, or didn't exist at all in affordable electronic form. Carburetors were known technology. Mechanics understood them. Parts were cheap. The tooling was paid for. Why rock the boat? Chapter 3. The German secret Ford was hiding. This is where Ford's European connection becomes interesting. While American engineers were stuck in the carburetor paradigm, convinced that fixed venturies and jets were the only way forward, Ford of Europe was playing with some genuinely weird ideas. See, European fuel economy standards had always been tighter than American ones because gas cost about 4 times as much. A gallon of premium in Germany in 1970 cost the equivalent of $3. In America, it was 70 cents. European engineers had been forced to think creatively about fuel metering for years, while their American counterparts were still building engines that got 12 miles per gallon, and nobody cared. The cultural divide was massive. American engineers thought in terms of cubic inches and horsepower. European engineers thought in terms of liters per 100 kilometers and thermal efficiency. American cars had V8s that made 300 horsepower and drank fuel like alcoholics at an open bar. European cars had 4 cylinders that made 80 horsepower and could cross the continent on a single tank. Different worlds, different priorities, different solutions. In the early 70s, a Ford engineer named Thomas K. Garrett, who'd spent time working with Ford of Germany on their Cologne F6 program, saw something that made him think. Bosch mechanical fuel injection, which was showing up on high-end Mercedes and Porsche models, used a sliding sleeve to vary the fuel delivery. The sleeve moved based on engine load, continuously adjusting fuel flow rather than relying on fixed orifices. It was elegant, precise, and expensive as hell, but the principle was sound: variable metering instead of fixed metering. Garrett had one of those light bulb moments that seem obvious in hindsight but revolutionary at the time. What if you could apply that principle to a carburetor? What if instead of fixed venturies and jets, you had venturies that changed size based on engine demand and fuel metering that varied continuously rather than in fixed steps? You'd get the precision of fuel injection with the simplicity and low cost of a carburetor. Best of both worlds. The idea was so simple, it was almost stupid. Almost. Garrett sketched it out on a napkin during lunch, literally. That napkin still exists somewhere in Ford's archives. A crude drawing of sliding Venturi pistons and tapered metering rods that would eventually become a production carburetor on hundreds of thousands of vehicles. He pitched it to Ford's Advanced Powertrain Engineering Group in 1972. The initial response was predictable and depressing. That's not how carburetors work. The tooling costs would be insane. Why fix what isn't broken? Holley will just copy whatever we do anyway. Every objection you'd expect from engineers who'd spent their entire careers working with conventional carburetors. Change is scary, new ideas are risky, better to stick with what works even if what works isn't working that well anymore. But Garrett was stubborn, or maybe brilliant, probably both. He kept pushing, kept explaining, kept showing the math that proved this could work. He finally got a small budget to build a prototype. Just enough money to machine some parts, assemble a working unit, and prove the concept. Or fail quietly without embarrassing anyone. Ford was hedging their bets, giving him just enough rope to either climb out of the hole or hang himself. Chapter 4. The Technical Wizardry Nobody Talks About. Here's where the technical wizardry gets absolutely insane. The variable Venturi carburetor, or VOZV as Ford called it internally, threw out basically every conventional carburetor principle and started from scratch. Instead of fixed venturies, the VV had cylindrical slides that moved up and down in the throttle bores. As engine demand increased, these slides lifted, increasing the venturi area. This meant the air velocity stayed nearly constant across the entire RPM range. Constant air velocity meant consistent fuel atomization. Consistent atomization meant better combustion. Better combustion meant lower emissions and better fuel economy. It was elegant, it was brilliant, and it absolutely should not have worked as well as it did. But here's the genius part. Instead of jets, the VV used tapered metering rods. Picture a needle that's fat at one end and skinny at the other. This rod sat in a precisely machined orifice. As the Venturi slide lifted with increasing engine demand, the metering rod lifted too, but it was tapered, so a thinner part of the rod was now in the orifice. Thinner rod, bigger gap around it, more fuel flow. The taper could be machined to any profile, giving infinite tuning possibilities. One rod could handle the fuel curve from idle to wide open throttle. No jet changes, no power valves, no secondary circuits. Just a mechanical system that responded to airflow demand. The whole thing was controlled by a spring-loaded mechanism that balanced intake manifold vacuum against atmospheric pressure. High vacuum, low load, slides stay down. Lean mixture, low vacuum, high load, slides lift. Richer mixture. It was completely mechanical, no electronics, no computers, just physics and precision machining, doing exactly what you needed, exactly when you needed it. Compare this to a Holley 4-barrel. The Holley has fixed ventures, primary and secondary jets, power valves, accelerator pumps, idle mixture screws, high-speed air bleeds, and about 20 other adjustments. It works, but it's a Rube Goldberg machine of compromises. The Quadrajet is even worse, with its variable secondary ventures that still relied on fixed jets and a spread-bore design that was packaging genius but tuning nightmare. The VV carburetor did everything these systems did, with about 1/3 the parts and 0 compromises. It was the right air velocity at every RPM, the right fuel metering at every load, all the time, automatically. Chapter 5. The dyno numbers. That changed everything. When the first prototype went on the dyno in 1973, Ford's engineers couldn't believe what they were seeing. On a stock 302 cubic inch V8, the VV carburetor produced identical power to a Holley 4-barrel, but with 23% better fuel economy in steady-state cruise. 23%. That's not a rounding error. That's not within margin of error. That's a complete game changer. Let me put that in perspective. The Holley 4-barrel was the gold standard, the benchmark, the thing everyone compared themselves to. Ford's engineers had spent years trying to squeeze another 2 or 3% fuel economy out of conventional carburetors. They'd tried smaller jets, leaner mixtures, different air bleeds, every trick in the book. Getting 5% improvement was considered a major victory. 10% was publishing a paper-worthy achievement. 23% was supposedly impossible. The test engineer who ran that first dyno session reportedly walked out of the room, came back 5 minutes later, and demanded they run the test again because the numbers had to be wrong. They ran it again. Same results. They swapped carburetors back to the Holley. Fuel economy dropped back to baseline. Swapped to the Vegivolapis. 23% improvement. It was repeatable, measurable, and absolutely real. The emissions numbers were even more shocking. Hydrocarbon emissions dropped by 31% compared to the Holley. Carbon monoxide was down 28%, and this was with no other changes. Same engine, same cam, same ignition timing, same exhaust system, same everything. Just swap the carburetor, that's it. One component change delivering emissions reductions that other manufacturers were spending millions trying to achieve with catalytic converters, air pumps, and EGR systems. The reason was simple but profound. The fuel distribution between cylinders was so even that they could lean out the mixture significantly without running into misfire issues. In a conventional carburetor, some cylinders run rich while others run lean because fuel distribution through the intake manifold is uneven. You have to tune for the leanest cylinder, which means the rich cylinders are dumping unburned fuel out the exhaust. Wasted gas, high emissions, terrible efficiency. The VV's constant air velocity meant fuel atomization was so good that every cylinder got the same mixture. You could tune it lean across the board without any cylinder misfiring. The throttle response was instantaneous because the venturi was always sized correctly for the airflow. There was no bog, no hesitation, no flat spots. Just smooth, linear power delivery from idle to redline. Stab the throttle, and the engine responded immediately. No waiting for the accelerator pump to squirt fuel. No secondary delay while the air door opened. The VV was always in the correct configuration for whatever the engine needed right now. Ford's engineers started testing the VV on different engines. Inline 6s, small block V8s, big block V8s. The results were consistent. 15 to 25% fuel economy improvement depending on the application. 25 to 35% emissions reduction. Identical or slightly better power output. It worked on everything. Ford's initial reaction was to keep this absolutely quiet. They knew they had something special, and they knew that if Holley or Rochester got wind of it before they had production tooling set up and patents filed, they'd be copied immediately. The VV project was classified internally. Dyno data was restricted to need-to-know personnel. The prototype carburetors were locked in a secure room when not in testing. Engineers working on the project were told not to discuss it outside the building. This wasn't paranoia. This was Ford protecting what might be the biggest carburetor innovation in 40 years. Patent applications were filed under vague descriptions, fuel metering device with variable geometry, instead of anything that would tip off the competition. The few suppliers who needed to be involved in prototype development signed non-disclosure agreements with penalties severe enough to bankrupt a small company. Ford was playing this close to the vest because they knew what they had. A weapon that could embarrass Holley, humiliate Rochester, and give Ford a massive advantage in the emissions and fuel economy wars that were just beginning. Chapter 6: Real-World Domination. By 1974, Ford had working VV carburetors on test vehicles. Mercury Capris with a 2.8-liter V6 were the first guinea pigs. These were small, light cars where fuel economy really mattered. The results were remarkable. Drivers reported smooth power delivery, no cold start issues, and genuine real-world fuel economy improvements of 15 to 20% over the conventional motorcraft carburetors. Even better, the VV carburetors just worked. They didn't need seasonal retuning. They didn't care about altitude changes. They were practically set it and forget it. Reliability testing was extensive. Ford ran VV carburetors for the equivalent of 200,000 miles on engine dynos. They cycled them through temperature extremes, simulated high-altitude operation, tested them with contaminated fuel. The failure rate was actually lower than conventional carburetors because there were fewer parts to break. The slides were self-cleaning. The metering rods were hardened stainless steel that showed that virtually no wear. The only maintenance required was occasionally cleaning the air filter and checking the float level. That's it. Ford started sneaking VV carburetors into production in 1975 on selected Mercury models and F-Series trucks with the 300 inline six. They didn't advertise it. There were no press releases. The carburetors just showed up on vehicles with no fanfare. Dealers were given minimal training. Basically, don't touch it. It doesn't need adjustment. Customers had no idea their carburetor was fundamentally different from anything else on the road. Chapter 7: The Industry Freakout. Here's where things get interesting. Holley knew something was up. They'd noticed Ford vehicles at emissions testing were beating everyone else's numbers with room to spare. Holley bought a Mercury Capri with a VV carburetor, took it back to their engineering facility in Michigan, and tore the carburetor apart. The lead engineer's response, according to internal memos that surfaced years later, was essentially, "What the hell is this?" Holley tried to reverse engineer the VV design. They built prototypes, they tested them, and they failed completely. The problem was precision. The VV carburetor required machining tolerances that were tighter than anything Holley's production equipment could achieve. The slides had to seal perfectly while still moving freely. The metering rod tapers had to be precise to within 0.005 of an inch. The spring rates had to be exact, or the whole system would oscillate and hunt. Holley's prototype VV carburetors worked on the bench but failed in real-world testing. They couldn't get the fuel metering stable. Ford had patents on every critical dimension and mechanism. Holley was locked out. Rochester had a different problem. The Quadrajet was General Motors' baby, and GM had invested tens of millions in Quadrajet production tooling. Even if they could copy the VV design, which they couldn't because of patents, they wouldn't because it would mean admitting Ford had out-engineered them. GM's response was to double down on the Quadrajet, adding more vacuum controls, more secondary metering rods, more complexity. They made the Quadrajet work well enough to meet standards, but it never approached the VV's efficiency or simplicity. Chapter 8: The Fatal Flaw. Nobody saw coming. By 1977, Ford had VV carburetors on multiple platforms. The 5.0-liter V8 and F-Series trucks got a larger VV variant. The inline 6 and Mustang IIs ran V-Buff carburetors. Even some Lincoln Continental engines used them. Ford was quietly building an empire of variable Venturi technology, while their competitors were still trying to make fixed Venturis work. Production volumes reached over 200,000 units per year. The tooling investment had been substantial, but the fuel economy improvements were letting Ford meet CAFE standards without downsizing engines as aggressively as G and Chrysler. Customer satisfaction was through the roof. Owners reported their Holley-equipped vehicles just worked better, smoother idle, better cold starting, no carb icing issues because the Venturi design prevented it, fuel economy that actually matched the EPA estimates, which was unheard of in the 70s. Mechanics who understood how the VVV worked loved them because they required almost no adjustment. Mechanics who didn't understand them were terrified because they looked complicated. And there's the fatal flaw. The VV carburetor was a victim of its own sophistication. It worked beautifully, but it didn't look like a normal carburetor. There were no jets to swap, no idle mixture screws in the usual places, no obvious adjustment points. The average shade tree mechanic, or even the average dealership tech, looked at a VV carburetor and had no idea where to start if something went wrong, which ironically was rare because they were reliable. But perception matters. Ford tried to address this with training programs. They produced detailed service manuals. They even created cutaway demonstration units to show mechanics how the VVV worked. But by the late 70s, the dealer network was huge, and getting everyone up to speed on a fundamentally new technology was like trying to teach your grandfather to use a smartphone. Possible, but frustrating for everyone involved. Some dealers, when faced with a VV carburetor issue, would just swap in a conventional motorcraft or Holley and call it a day. Easier than learning something new. The complexity perception killed the VV's expansion. Ford had plans to put VVV carburetors on every engine by 1980, but feedback from dealers was consistent. This is too weird. Customers don't trust it. We can't service it properly. Never mind that it required less service than conventional carburetors. Never mind that it worked better. It was different, and different is scary. And Mr. Chapter 9. Why fuel injection killed the greatest carburetor ever made. Then electronic fuel injection happened. By 1980, the writing was on the wall. Bosch had developed reliable electronic fuel injection systems. They were expensive, but costs were dropping fast. More importantly, electronic fuel injection could do everything the VV carburetor could do and more. Individual cylinder fuel control, closed-loop operation with oxygen sensors, adaptability to changing conditions in real time, the ability to compensate for altitude, temperature, fuel quality, even engine wear. The VV carburetor was mechanical genius, but it couldn't compete with computers. And here's the thing that really stings. The Versa Iron Feet carburetor had proven that continuously variable fuel metering was the answer. That's exactly what Ford's engineers had been saying since 1972. But electronic fuel injection did it better. It didn't rely on manifold vacuum and springs tension. It used sensors and processors that could make hundreds of adjustments per second. The VV could adapt to conditions. EFI could predict them and adjust before they even happened. Ford's bean counters did the math. They could either invest millions more in VV carburetor production expansion, dealer training programs, and public education to overcome the too complex perception. Or they could jump straight to the technology that was clearly the future. Electronic fuel injection was coming, whether Ford liked it or not. Emission standards were getting tighter every year. CAFE requirements were becoming more stringent. The VV carburetor was brilliant for 1976, but by 1981, it was already being outclassed by early EFI systems from Bosch and Bendix. The decision came down from the top. Ford made a strategic choice. Instead of investing more in VV carburetor development and dealer training, they jumped straight to fuel injection. Why teach thousands of mechanics how to service a sophisticated carburetor when that carburetor would be obsolete in 5 years anyway? It was cold, calculating, and absolutely the right business decision, but it killed the VV program dead. By 1983, the VV carburetor program was essentially a zombie. Existing applications continued because you don't just shut down production lines overnight. But no new development happened, no new applications, no improvements to the design. The engineers who'd pioneered the VV technology were reassigned to EFI development, where their expertise in precision fuel metering actually proved invaluable. The VV carburetor became legacy support, maintained but not advanced. By 1987, the last VVI carburetor rolled off the production line. One of the most sophisticated carburetors ever designed vanished with barely a whimper. No press releases, no celebration of its achievements. No acknowledgement that Ford had created something genuinely revolutionary. It just stopped being made. Dealerships ran through their remaining stock. Rebuilders bought up the last service parts. And that was it. The irony is almost painful. I mean, come on. Ford had created a carburetor that solved every major problem with fuel metering. It was more efficient than Holley. It was more precise than the Quadrajet. It was reliable, simple to manufacture once you had the tooling, and it actually worked as designed. The VV carburetor did what Detroit said was impossible. It made a carburetor that could handle emissions, fuel economy, and performance without compromise. But it arrived at exactly the wrong moment in history. 5 years earlier, before emission standards got serious, and it would have dominated the carburetor market. There would have been no competition. Holley and Rochester would have been forced to license the technology or go obsolete. 5 years later, and carburetors themselves would already be dead, killed by fuel injection. The VV carburetor existed in a tiny window where it was both revolutionary and doomed. It's like watching someone invent the world's best cassette tape in 2006, right as iTunes was killing physical media. Brilliant execution, perfect engineering, completely irrelevant timing. The VV carburetor was the technological equivalent of arriving at the party right as everyone else is leaving. You're dressed perfectly, you brought great snacks, and nobody cares because the party's over. Chapter 10: The Legacy and What We Lost. Today, variable Venturi carburetors are collector's items. Vintage Ford truck enthusiasts seek them out because they know the VV works better than any aftermarket carburetor you can buy. The few mechanics who really understand them guard that knowledge like trade secrets. There's a small but dedicated community of VV carburetor rebuilders who machine their own parts because Ford stopped producing them decades ago. These carburetors that were once considered too complex are now prized for their elegance. What did the VV carburetor prove? It proved that Ford's engineering department, when given freedom to innovate, could beat the established players at their own game. Holley had decades of performance carburetor experience. Rochester had the resources of General Motors behind them. Ford had one stubborn engineer with an idea and just enough budget to prove it worked. That's all it took to create something genuinely revolutionary. The lessons are timeless. First, sometimes the established way is just the established way, not the best way. Holley and Rochester had convinced everyone that fixed Ventures and jets were the only viable solution. They were wrong. Second, precision execution matters more than complexity. The VV carburetor was mechanically simpler than a Quadrajet, but required much tighter tolerances. Third, innovation means nothing if you can't support it in the field. The VDVS failed not because it didn't work, but because Ford couldn't get their dealer network comfortable with it. There's also a broader point about timing. The VV carburetor was ahead of its time in the 70s, but would be obsolete by the 80s. Sometimes being first just means you get to be the cautionary tale for whoever comes next. Ford's investment in VV technology taught them about precision fuel metering, which absolutely helped when they transitioned to electronic fuel injection. The knowledge wasn't wasted. It just transformed into something else. Looking at modern engines with direct injection and variable valve timing, you can see echoes of the VV philosophy. Continuously variable systems that adapt to demand in real time. That's what the VV carburetor was doing mechanically in 1976. Ford was 40 years ahead of the curve. They just didn't have the electronics to fully exploit the concept. Imagine what a VV carburetor with electronic control of the slide position and metering rods could have done. But that's essentially fuel injection at that point, which is exactly what replaced it. The variable Venturi carburetor story is one of those historical footnotes that deserves to be headline news. Ford quietly out-engineered the carburetor establishment, proved that better solutions existed, and then watched as history moved past carburetors entirely. It's a reminder that sometimes the best answer to a problem arrives too late to matter. That genius can be ignored if the timing is wrong. That innovation requires not just engineering brilliance, but market readiness and support infrastructure. Every time someone argues that the old ways are the best ways, that conventional solutions are good enough, that innovation is too risky or too expensive, remember the VV carburetor. Remember that one engineer with an unconventional idea beat Holley and Rochester at their own game. Remember that precision and elegance can triumph over brute force and complexity. remember that Ford, of all companies, created the most sophisticated carburetor in history, and almost nobody knows about it. The VV carburetor sits in automotive history as proof that the underdog can win, that established players can be beaten, that better solutions exist if someone is brave enough to pursue them. It also sits as a warning that timing matters, that support infrastructure matters, that being right isn't enough if the world isn't ready for you. Ford's secret trick wasn't just a better carburetor, it was proof that questioning fundamental assumptions can lead to breakthroughs. And sometimes those breakthroughs change everything, even if nobody remembers them 30 years later. So, here's to the variable Venturi carburetor, the carburetor that Holley couldn't copy, that Rochester couldn't match, that mechanics couldn't understand, and the history forgot. The most elegant solution to fuel metering ever devised, killed by its own sophistication and terrible timing. Ford's greatest carburetor achievement, hidden in plain sight on thousands of trucks and cars, working flawlessly while the world moved on to fuel injection. Sometimes the best ideas don't get to win. Sometimes they just get to be right. And maybe, just maybe, that's enough.